Today's Jacoby-Tarbox Insights is going to focus on hygienic joint design, specifically within the Jacoby-Tarbox Hygienic site flow indicator. We're going to start today by reviewing the video of the concepts behind the Hygienic joint design.
Hygienic site flow indicators allow the operator to clearly see their process and look for specific features in the flow, such as color, clarity, contamination, or air entrainment. These processes vary greatly and may contain particles or contaminants that must not be allowed to gather and be trapped. The positive stop design, Acme threads, and locating O-ring of the high site work together to minimize O-ring intrusion and maximize cleanability. Traditional units have up to 5 times the O-ring intrusion of the high site, drastically increasing cleaning time, the chances of trapping material, and the potential for contamination. Avoid the traps and problems of traditional units. Cleanability matters, and the Jacoby-Tarbox high site's minimal O-ring intrusion from its precision alignment has performance you can see.
For today's discussion, we're going to specifically focus in on the glass to metal joint. Not as easy to see here, so we use some slides to further illustrate this concept. In our first slide, we show small black dots just to represent some amount of material that might be unwanted within the process. Again, this could be something that settles out during the process or just simply trying to clean out the piping after your product has been produced. In the traditional unit on the right, you see where an elastomer has been compressed, causing that material to extrude into the ID of the system, causing a ridge or a bump. In the high site design, you'll see that the elastomer is compressed as well, but doesn't extrude quite as far out. In this system, the fluid travels over a more tortuous path as there are both indentations and extrusions over which it must travel. In our second slide, we really focus in on the details of how this path causes turbulence in the liquid. In a traditional system, the fluid flow is very laminar, meaning it's slow, it's smooth, it travels along the surface, and by definition, actually is not moving at the surface internally in the piping. This allows it to leave material behind. As velocity increases, the difference between the ID flow and at the edge is even more dramatic, allowing it to leave more material behind. So the analogy is similar to that of a roller coaster. Going up a large hill and then going down, and if the track were not holding the coaster in place, it would actually allow you to lift off and be removed from it. Very similarly, the laminar flow goes over the large intrusion and then later settles back down. But the entire time it's been away from the wall, it leaves material behind and allows it to simply settle in place and not be touched by the process flow. Increasing velocity makes this case even worse as you go. Within the high site, because the hills are small, it's like the end of the ride, where you suddenly go into the gatehouse and they catch you with those last couple of hills, jerking you up and down very quickly. When this happens, it causes turbulence of flow inside the high site. This strong vertical upward and downward movement creates small currents inside the liquid, thus removing any debris or settled materials and allowing the system to be completely clean. The concept of introducing turbulence into a piping system is nothing new. While the joint design in the high site does it in a little bit different way, the concept is similar to that of European standards DIN 11864 and DIN 11853, both of which introduce turbulence for improving joint cleanability. The minimal intrusion and slight indentation in the high site design introduces turbulence while also minimizes the amount of potential liquid holdup to maximize joint efficiency and also system cleanability. The faster the system's clean, the faster you're up and running, producing more product.